Lesson 5 is on midpoints and diagonals in quadrilaterals. This is the last lesson in this unit. It's more of an investigation again, and it would be kind of more meant to be done in class together with rulers, and you can kind of work through this on your own. But anyway, if we were going to measure the four sides of the following quadrilateral and mark the midpoints, so we learned in our last lesson that a midpoint is halfway along a line segment right in the middle. So I did have a ruler and I measured the lengths of these sides and I found the midpoint of each side. So it's a little hard to do on a computer here electronically, but if I found the midpoint of AB, I labeled it E and then F, G, H. And this was kind of an odd shaped quadrilateral here. I used these different symbols on every side because none of the sides are actually the same length. Then it says draw line segments joining E to F, F to G, G to H, and H to E. So then what type of quadrilateral does EFGH appear to be? Well, to me, even though this was sort of an odd-shaped quadrilateral at the beginning, this to me kind of looks like it's a parallelogram inside. And then it says, measure and compare the line segments in the smaller quadrilateral. What relationships are there among the lengths of these line segments? So you could print this sheet out yourself and you could get a ruler and you could measure and make sure that these are actually the midpoint of each line segment. When I measured the line segments here inside on paper, I found that this side was 4 centimeters and this side was 4 centimeters. And then I found that the opposite sides here were each 5 centimeters. So that's kind of going in line with thinking that this is a parallelogram, just because the opposite sides are equal in length. And then measure the interior angles of the quadrilateral with a protractor. So I did hunt around and I did find a protractor. When I measured the interior angles of this interior quadrilateral, I found that this was pretty close to 125 degrees. It was an obtuse angle, and so was this one. And then I found the opposite two angles were both 55. So two angles of 125 and two of 55 actually add up to 360 degrees. And then are any of the sides of the quadrilateral parallel? So we learned this co-interior property. If co-interior angles are supplementary or they add up to 180, we know that the line segments are parallel. So when I look back up here at this C shape, so remember this C shape we talked about before? When I look inside the C, 125 plus 55 is actually 180. So I know that the lines are actually parallel and I'd be able to mark opposite sides with little arrow symbols so that I can show that the opposite sides are parallel, and we do have a parallelogram. So this is the first property that you need to understand about quadrilaterals. I think it's kind of interesting because it doesn't matter what the four-sided shape looks like that you originally start out with. If you join the midpoint of each line segment together, you end up with a parallelogram on the inside. If you want to test it out, you could try drawing a few different strange looking quadrilaterals and then join the midpoint of each side together, and you end up with a pretty straightforward parallelogram on the inside. For the following parallelogram, draw a diagonal from A to C and measure the length of the diagonal. Then we're going to draw a diagonal from B to D and measure that length. So we can kind of talk about that first. This is another property of quadrilaterals, actually a property of parallelograms that we're going to talk about as well. What do you think? If I draw a diagonal from A to C, do you think it's the same length as the one from B to D? And I mean, different properties are true for different shapes. If we had a perfect square, we could imagine that the diagonals would be exactly the same length because we have a square. And also that the diagonals, when we have a square, for example, the diagonals would meet at 90 degrees to each other. So a square is different. We could also look at the diagonals of a rectangle and imagine that if I drew diagonals across on a rectangle, do you think those would be the same length? So a rectangle, to me, it looks like they're going to be the same length, those two diagonals that we might have. But now you can see that it doesn't, it's not necessarily true that we have 90-degree angles here in the center. So if it was a rectangle, the diagonals are the same length. If we have this parallelogram, do you think the diagonals look like they are the same length? Kind of interesting because AC to me looks like it's a little bit closer together than B to D. So label the intersection point E. So we have E in the middle. And then measure the length of A to E, B to E, C to E, and D to E. So we want to measure the lengths of these smaller line segments from the outside vertex to the center here. So what we end up noticing is that A to E and C to E is the same length, and then a different length, D to E and B to E. Those are also the same length, but they're longer than the distance from A to E. So if we imagine drawing two diagonals of a parallelogram, what's interesting about that is that this E point in the center here bisects each line segment. So if you wanted to find the exact middle of B to D, you would just draw the diagonal going the other way, and those line segments then get bisected. So just two key concepts, and that's it for this lesson. Joining the midpoints of the sides of any quadrilateral produces a parallelogram. So this is the one that I think is kind of cool. Again, this is sort of an odd-looking quadrilateral here, and when we join the midpoints of each side length together, what we end up on the inside here with is a nice parallelogram. Another property is that the diagonals of a parallelogram bisect each other. So if I want to find out where the center is, I can just draw two diagonals, and the length of the diagonal is bisected so that this length here is the same as the length down here.